Well, hello there, YouTubers and fellow beginning programmers. So today I wanted to make a video on creating a game, and I want to cover the casual game fundamentals. So let's take a look at what these fundamentals are. So the fundamentals of a game, of a casual game, are composed of drawing on a coordinate plane. You may be used to drawing on a coordinate plane from your math classes from high school or middle school. And you know that you have an XY coordinate system. We're going to be covering that and how that works in the Windows system because it may be actually a little bit different than what you're used to. So there's another concept of getting non-blocking input. So in the game, when you're playing the game has to go through the steps of rendering the game, drawing the game, executing the game logic, and not necessarily in that order, but it's going to execute those steps, and it has to be getting input continuously. So in order to understand that, we really have to understand the game loop. So we're going to be talking about that a little bit. Another thing that gets new developers that get into gaming, into game development, that trips them up is that separating the game logic from the drawing. So it's kind of separated. When you're just looking at a video game, you're seeing something moving around the screen and you don't really know what's going on. So we're going to break that down, and that also ties back into the game loop, and we're going to take a look at how that works. And we also have an example. We're going to be understanding the game loop. So we're going to take a close look at the game loop. And another important point in this is that you wouldn't really have a game if you didn't detect some kind of collision, something that the game interacts with. So we need to detect the collision of the game. Not all games have collision detection because not all games crash against each other. You could be creating a game that is composed of something else, like maybe a keyboard typing game or a hangman game, and those don't necessarily have collision detection. But in most games, you actually do have collision detection, so it's important to know what those things are. And one final thing that I wanted to talk about is controlling the frame rate. The frame rate is basically what determines how frequently your game refreshes. So typically a good game will refresh at rates faster than 30 frames per second. And sometimes maybe 60 frames per second in real consoles, maybe more, I don't know. But I think they're pretty fast, but a good frame rate might be 30. In our case, with this example, we're only going to be refreshing at 10 frames per second. So, but you have to control that, because if you don't control the frame rate, the game loop will execute just as fast as it can process, and that may make your game too fast. So you have to control the frame rate. So the first thing that we want to talk about is the game loop. Keep in mind that the game loop, this loop from top to bottom, if you notice, we have the steps. First, we clear the screen, and that's sort of, if you can think of it like our canvas. If we have a canvas that we can draw on, and we clear the entire screen, so we clear it completely, then we can get input if available. Keep in mind that input has to be non-blocking, so we look to see if there's input. In a real software development kit for games, you can actually check for keyboard input, mouse input, joystick input, whatever other device of input you may have. It will check for that input. If it's available, it gets it. It does not wait for it. It does not wait for the user to enter input. If the user, it's I don't want to say it's asynchronous, but it's non-blocking. So it just gets it, and if it's there, it checks to see if the key's pressed or whatever. And if it's not there, it just keeps trucking along. So then the next thing you want to do is you want to update the game objects. So what are the game objects? The game objects are typically any enemy ships, any enemy shooters, any bullets that are flying around the screen, any rocks, objects, anything that the game does. And typically that's your AI, whatever the game does to move things around the screen, you update those, and you update them incrementally. So for example, if you have a ship that's moving in your direction from top to bottom, maybe you increment it by the speed. So for example, the speed may be that it's moving at 10 pixels per frame. So you increment its Y position by 10, and that'll move it down on the screen. And you notice that I said down and not up because you're adding 10, you're moving down, and we're going to talk about that because the XY coordinate system on the Windows system is not in the quadrant that you think it is in. So it's moving down. So you update your game objects. Next thing you do is you update your player according to the input. So whatever input, so for example, if the player is moving left or moving right, you check for that input. Earlier, you got that input. Now you have to take that input and determine which direction to move your player, or if your player is kicking or fighting or shooting a bullet, then you initiate that action. Finally, you check for collisions, and collision detection is something that can be very simple or can be very complicated depending on how you want to look at it. But if you think of collision detection, it's just two objects that intersect with each other. So for example, if you have two squares and if they touch each other, if they intersect, you just have to check all their positions. How do you do that? Typically, you can draw a shape around an object, like for example, like I said, a square around the object or a rectangle. And if anywhere of those 2 points they intersect, then that's your collision detection. Finally, you get to the last step. So far, everything you've done up to this point is logic. Everything is logic. Then on the draw screen, that's where you draw every object with its new position, its updated position, and you're going to be drawing on the XY coordinate system. So you draw everything. So we're going to take a look at how things work, and let's take a look at a quick example of a game that I've already created. For this example, let's take a quick look and see what we're talking about. In this example, I'm just running the game from the command line, and you notice this is just a regular old command line. I'm using a console emulator, but it's just your basic command line. It's the Windows command line. Unfortunately, this game will not play on Mac or Linux because it has Windows-specific libraries. But the first thing we want to do is compile the game. So I call the game Pong C, but I have to use the GC compiler. So Pong C, and just use the commands to execute it. And I'll call it g6.exe to make sure that I have the right game. And then I execute it. Now what this game does, it actually draws right on the console. I'm getting the handle to the console output and drawing on the console screen. I'm not using an extra canvas or an extra window or anything like that. It's actually drawing right on the console. So and this is not typically how you would write a game because it's too slow, it's not really fast, and the downside to the console is that your XY coordinate system kind of breaks apart because the console has the concept of rows and columns. So when you move a whole row, that's a whole character over. Typically in a real SDK, you can actually move small pixels at a time, which gives you a lot more granularity for your game. But in this case, I can only move one row and one column at a time or more. So it makes it a little bit difficult, especially with the frame rate, because I have to slow down my frame rate to be slower, because when I move one, that's quite a distance. Even though you don't think about it, each frame is moving too far. So let's go ahead and execute our game. And this game doesn't really do much, but it's enough to demonstrate all the fundamental concepts of creating a game. So right now I'm controlling the bat at the bottom with my keys, the J and H keys, and as you can see, and that's not doing much. And I'm also, if you notice, I'm also keeping track of the score. Every time I hit the ball, it keeps track of the score, and I'm keeping track of the lives and displaying everything on the screen. So if I let the ball go, you notice that the lives are going to go down, and the lives just went down to 2, and I got a oopsie displayed on the screen. So when I hit it, it displays, oh yeah. And so now if I let the ball go down again, it's going to bring my lives down. And so it brings the lives down and it displays oopsie. So now let's finish and the game is over. So now the game is over. I can hit quit to exit and bring me back to the console. So that's an example of the game that we're creating. And I'm going to talk about the concepts that I discussed with actual game code, and I'm going to post the game code in the description of this video. So if you go to the description of this video, you will see the code and you can actually get it. It's just one file. It's not really a big deal, but I'd be interested to see if you can modify the file to create your own game, because all the basic ideas are there. A lot of the research that I had to do to make this work is already there. So then you just have to do some of the logic, which I'm not going to underrate logic, because logic can be very complicated if you're doing anything like any kind of math or trig or anything like that. And some things that are more complex, then you may have a hard time with it. But at the same time, some of the hard lifting, it has already been done for you. So let's take a look at something else that I want to talk about, because it's the coordinate system, and it's very important because Windows has a different, I don't want to say that a different coordinate system, but it actually draws on a different way than you expect. So let's take a look. So the Windows coordinate system is, it's like any coordinate system you would expect. It has the X and the Y. The thing that's different about the coordinate system is that you would think, and it's kind of screwy because it's not what you would expect. So the Windows coordinate system works a little bit different, because when you draw on this quadrant of the screen. If you think of this portion right here where I'm putting my mouse cursor, this portion where the 0, 0 is, that's the top left hand corner of your screen, and to the right of that is positive 1, 2, 3, and so on, and down from that screen, down from that is positive 1, 2, 3, and 4. And I'm not sure of the thinking that went into play when they designed this a long time ago, but that is the way that it's drawn. Maybe it has something to do with lower level electronics. I don't really know, but I'm sure there's a good reason for that. But just keep that in mind when you're drawing on the screen, that you're going positive this way and positive down. So if your objects need to move down, they have to increment on their way down. In our example, we're using the console, so we are moving one row down at a time, and we can't move any less than that. And not to my knowledge anyway. It's maybe possible, you can research it, but I think you can only move one row down at a time, and the same way you can only move over one column at a time. So let's go ahead and take a look at some code, and let's talk about those concepts in the game. As I said earlier, this is just one file that has everything in it. And typically in C, if you've done anything more advanced, you know that you break your file apart into several files. But I didn't want to do that in this case, because I wanted to put everything in one place. The other thing that I didn't want to do is start creating a bunch of structs and everything and get any new programmers lost in the logic. So I didn't create any type of structures that you can combine a lot of these variables and values into, and that would have been really the best way to go ideally, but I didn't, like I said, I didn't want to do that to confuse anybody coming on board and intimidate them with structs and different things, even though that I still can totally avoid structs, because some structs are required by some of the things in the Windows and the ConIO. So starting off, you notice that we have the libraries. Of course, this typically you have the stdio, and you do anything more than your simple hello world and you're going to need stdlib. We also have windows.h, because we have some functions out of the windows.h library, such as putting the game to sleep, calling sleep, and we can tell it in milliseconds. I believe that the std library also has a sleep method, but I think it's in whole seconds, so we need the windows.h in order to do that. The other thing that we needed was the ConIO, and the ConIO is because we need to get a hold of the console handle in order to draw to the screen. And finally, we needed the string.h to copy strings, because remember, in this is a console game, and everything that we're doing consists of manipulating and drawing strings to the screen. That's all we're doing. We're not drawing anything else. We're not drawing images. We're not drawing at all. We're just putting out strings to the console. So everything that you see in the game is actually an actual string. So just keep that in mind. So a few things that I had to create initially, and this is so that we can draw to the screen. So I created this function, print@xy, and print@xy, if I can find it, you notice that it does a couple of things. So the first thing it does, it gets the coordinate, and this is coming out of, I believe, I think it's coming out of ConIO. I want to say it's ConIO. I'm not 100% sure, but it's a struct, and the struct has an X and a Y coordinate. And so I just tell it, give it the X, Y coordinate. So wherever you want to draw on the screen, you give it a X, call this function, give it an X and a Y coordinate, and it's going to draw. And keeping in mind that the X, Y coordinate, Y goes down, it starts from 0 and goes down, and X starts from 0 and goes to the right. So incrementing as they go. So the first thing we want to do after we set the X, Y coordinate, we want to set the console cursor position. And this is going to tell the console, hey, place your cursor position here, anywhere on the screen. It has to be valid, right? So we put the console, and of course we got the output handle, so don't worry too much about that for now. I'll show you where I got the output handle. So we tell it to put where to put the console position and pass it the coordinate parameters, and then anything we print will go to that location in the screen. So that's how that's done. And I created this flush, not 100% sure that it's working, but I created the flush because I wanted to make sure that everything gets printed out to the screen when I tell it and not when it wants to. So that's that. The other thing about this is where I got the actual handle, and you'll see that the handle is a defined type. And here's the output handle. And one of the first things that I wanted to do, since we hide the cursor, and this might be a bad practice to put it in there, but anyway, when we hide the cursor, the first thing we want to do is get the handle, and this is getting the standard output handle. So this is what we're going to use throughout the game to write out to the screen. And one of the things that we want to do is, of course, we just give it a few parameters, and for the size and to hide it, basically, because the reason for that is because you notice that wherever I put my handle, it will put it. But you notice that if I'm in my console here, you don't see, I'm clicking, but you don't see an actual cursor there. So if I actually go to open a new console, you notice I have a cursor, but in my game, since I hit the console, it kind of hit it, it's kind of global, and it just kind of hit the cursor because we don't want to show that cursor during our game. So if we go back, so that's the first thing we did. We hide the output, the cursor. So there's a lot of logic, and you can see, and don't let this intimidate you. It has a lot of things going on, but if you really look at it, there's a lot of values and variables that we have to store because we kind of have to tell it. One of the things is that with the game, it has to know its bounds, where in the screen, how far in the screen, whether you want to scroll through the screen, and all these different things. So in this case, we needed a couple of settings for the screen width and height. And really keep in mind that screen width is in columns and height is in rows. So we just had to kind of tell it. But right now I'm not setting them because I'm going to do that in the screen width. So the other object that we have in our game is the bat. And the bat's going to have to know its X and Y location or position or coordinates so that we can draw it on the screen. Another thing that we have is the bat width and the bat speed, because bat has to have a width, and that'll come in handy later on. So, and you'll see where it comes in handy. And the bat speed, anything that moves on your screen has to have some kind of speed. Typically, the speed is not so much speed like so many, because you already know that you're moving at, so many frames per second. But typically, it actually translates into this many pixels or this many units per frame. So if you say, for example, that the bat speed is 2, in my instance, it's 2 rows or 2 columns, right? In my case, it's 2 columns since the bat is only moving left to right. So it's moving 2 columns per frame. So if I give it a 1 or a 2, it'd be 1 column per frame or 2 columns per frame or 3 per frame. And that's typically what we would consider speed. So it's moving so many units per frame. So the other thing that we have to know is the ball X and the ball Y, because we have to draw the ball on the screen. It has to update with every frame. The lives, of course, if we lose lives, we need to know that. And the game state. This is something that's pretty important because typically when you think of a game, you always think of a game as playing. But keep in mind that when you play a game doesn't start off playing. A game usually starts off in some kind of pre-start position, whether that's actually configuring it or maybe even before configuring, kind of maybe just in an idle mode. And then when you start a game, maybe it doesn't go right into the gameplay. Maybe it goes into configuring some of your characters or your settings or whatever the case may be. So the game state is pretty important because you don't necessarily want to execute that. But even in those idle states, you still need to draw the game and you still need to update things, and maybe you still need to capture input. You're just not in actual, let's just say, fighting mode. So the other thing is, of course, you don't want to hard code any values. So like in this case, we have game state. In this case, we only created two game states, game state over and game state playing. But of course, in a real game, you would probably have a lot more game states. And the goal points is just to increment so many points per every time you strike the bat. And these delta X and delta Y, because some, like in the case of the bat, I just gave it speed because it's only moving horizontally, left and right. But in the case of the ball is moving, it's moving in 2 dimensions. It's moving X and Y. It's constantly updated. So that's why I created delta X and delta Y. And you can think of that as the speed X and speed Y. And those could be different from one another. So it could potentially be moving at 1 in the X plane, but it could be moving at 2 in the Y plane. So just something to keep in mind. Of course, the score, and we have something for the ball string and the bat string and the game over string, just so that we don't hard code any values. One more thing that we did was create these previous locations, and I'll get more into that, but just keep those in mind. Why am I storing these previous locations for the bat and the ball? Well, we'll see when the time comes. So before we do that, let's go ahead and get into the game a little bit, and let's go ahead and into how the game works. So the first thing we want to do with the game is initialize. And what we do in the initialize, in the init method, and I define all the methods down below, is basically initialize all the values. I want to initialize all my values. So here I'm initializing my goal points to 10, my game, and these are sort of my constants. I drew them as constants, but they're not really constants because I'm actually setting them. And the reason I have an init is because down the road you may actually want to load these things from a file. Right now I'm not doing that, but if you wanted to do that, you can always change it. That way you don't have recompile your game. You can actually load everything from a file. And that's important when it comes to testing, because you may want to change things that you don't want to have to come back and change the code. Or if you hand it out to someone to test it, they're able to change that without actually knowing anything about code. So anyway, so these are my settings: game state, screen width. We have to tell it the screen width and so on, and the bat speed. One thing about the bat is we want to start out in the middle, so that's why you see this screen width divided by 2 and minus the bat width. So you want to set it to the middle and then back up half the bat width. That way it's really truly centered in the screen. Same thing with the ball. The ball starts where the bat is. And of course there's some of those variables, some values. So that's the first thing we do, is initialize the game. And then notice that we get here into the game loop. And in the game loop, which ends here, is basically every time this executes, this is 1 frame. All of this is happening with 1 frame of the game. And so we have a lot of logic here. One of the things is the clear screen method, which we'll get into in a second. And then we check to see if we have 0 lives. And 0 lives just checks to see if the lives are 0. If they are, then we set the game state to over. We change the game state, and we display enter Q to quit. So it's pretty self-explanatory. But the next thing we do is we get the user input. And after we get the input, if there is input, remember this is not blocking. This is not going to wait for that to come back. So in the case of the get input, if it doesn't have anything to send back, it might just send back something empty, right? So if we take a look at our get input function, get input function is, I'm setting it to 0, and I'm checking to see if there is a hit, a key down, and then I get the value. If there is no value, it's just going to keep trucking along and return 0. So keep that in mind as we go, because it's not going to wait. It's just going to keep trucking along. If there's no input, it just keeps going. Of course, it executes this logic to see if the game was already set to over and somebody pressed the Q to quit. It clears the screen and breaks out of the game loop. here we get into our game loop and we can see if the game state is playing. First thing we do is we clear the screen. You notice we capture the previous position. And the reason that we're doing it this way is because we're actually clearing the screen, but notice we're not calling system clear. We created our own clear screen because what we're doing is we actually overriding whatever we drew on the previous frame. We are clearing just that piece. The reason for that is because when you clear the entire screen with the console, it flickers. It's too resource intense. So I didn't want to keep doing CLS clear like we did up here because it'll create a lot of flicker. So what I did instead is I just draw a blank string over where I do the bat and where I do the ball. And then that's why I capture the previous position here. So when I clear, I'm clearing the previous position. I capture my previous position here so that I have it. And that way, once I update, of course, the positions are going to be now different than the previous. And the previous position is what I'm going to take on the next frame to use it to clear the screen. And of course, some of these things are, I'm going to check to see if the ball collides with the wall. If it does, all I do is I reverse, and the walls are only on the sides. So if it is, then I'm going to reverse the X direction. The delta X is going to switch. Times equal -1, all it does is switch it. So if it's, for example, 2, it'll switch it to be -2, so it'll start moving in this direction. If it's -2, if it was moving in this direction, then it's going to make it a +2. So that's all that does. Same thing with ball collides with ceiling. All it does is adjust the Y, so it'll bounce off the ceiling. And ball collides with bat, that's a very simple function, and we'll take a look at that in a second. If the ball collides with the bat, it displays the message, "Oh yeah," and that message is sticky. It stays there because I'm not necessarily erasing that when I clear the screen, but it kind of gets cleared because the ball will cross paths with it at some point and kind of clear it out. So finally here we have if delta X Y is greater than 0. So I mean, if delta Y, so that means the ball, the delta Y is greater than 0, that means it's moving down. So if the ball is moving down, I go ahead and reverse it. So it hits the bat. If it's moving down, I reverse it. And the reason for that is because you're going to find this quirk in a lot of games is that when you get into game development, a lot of times when you check your collision detection, sometimes your speeds and everything may actually cause two things to overlap. So for example, what I mean by overlap is when you have something like where let's say I got XXX here and I got, and then I got, let's say A for lack of better terms. I was going to use Y, but I don't want to do that. And so sometimes, and then I got AA and so see, you may expect the collision to happen right at the edge, but sometimes the collision doesn't happen at the edge. It might happen dead inside of that location. So what happens is that now they're not equal, and so now you say, okay, well, if they're in there, switch the position, but guess what? It might only move it back so far, and it doesn't move it back far enough, and now you're stuck in that loop. So that's why we're checking to see if it's actually on its way down. Then we reverse it. But if it's on its way up and it's still colliding, we don't care. We're not going to reverse that. It needs to go up. So the ball, when it strikes the bat, needs to go up. And that's really all that is, and that's why we're making that check. And for incrementing the score, of course, we just increment the score by whatever points. We just call that. And to see if the ball is out of bounds, the ball is out of bounds when it goes down. We decrement the lives, we reset the ball, we immediately start playing. Typically here you would have some kind of timer to, allow the player to get ready again and all of that. So I didn't do that. That would add a lot more complexity to the game, but typically that's something that you would do. Finally, we get to the one of the final steps is to draw. And you'll see the draw. The draw is something very simple. And then, of course, after you draw, you sleep for 100 milliseconds, which will bring you to a frame rate of 10 frames per second. So let's take a look at some of these important things a little bit closer. Let's work our way down and take a look at, you notice reset ball doesn't do anything but reset it back. Zero life, very simple function. Checks to see if there's 0, returns 1, otherwise it returns 0. Nothing spectacular there. Setting game state over, just sends it to that value game state over. When we update the ball, notice how we add, no matter what, we just add. Ball X add, Y add. You would think that it would always go to the right. However, keep in mind that sometimes delta X is negative. So when we add a negative to a positive, what happens to it? It moves to the left, right? Because if we're at 50 and we add -2, it's going to be 48. Same thing with the Y. If it's negative, it's going to move up. Well, in this case, because, it moves, the coordinates move down. So all we do is we update it. That's simple. So for getting input, you notice that I got the character. I set it to 0. I check to see this KB hit comes from I believe, Con.io. And all it's doing is checking to see if a key is pressed down. If the key is pressed down, it will attempt to get a character. Now, this call is blocking. It will block, but if a character is there, it's going to just fetch the character there anyway. So it's going to fetch that character and return that. And we're not checking mouse input or anything. We're just checking straight keyboard input. So KB hit, it checks to see if a key is down, it gets the input and it keeps trucking. If it's not down, it just keeps trucking and returns a 0. So, but it's not going to wait. It's not going to block our game or keep our game from executing. And you notice something very simple. Our update player, when we go to update player, we pass it the input that was captured in the KB hit, and we're using the J and the K keys to move left and right. And what we do here is if they press the J, we subtract. In other words, we move it to the left. If they press the K, we move it to the right by the bat speed. The other thing that we have to do finally here is to check that we don't move out of bounds. So if the bat X move beyond the 0 position, which is the leftmost part of the screen, we just set it to 0. In other words, we're not letting them go past that point. Same thing with the right. This is a little more complicated logic here, but essentially what we're doing is we're checking the bat. Say our bat's here, so it's taking, our bat has a width, but our X is here and the screen is here, so we have to make sure we actually check the right edge against the screen width, not the left edge, because the left edge would still allow it to go off the screen. So we have to take the right edge to see that it's not going off the screen. If it is, we reset it to that left edge of the screen minus the bat width, which is gonna not allow it to go past that. Ball collides with bat. This is part of the collision detection that we talked about. And you notice here, the first thing that I want to do, I want to see if the bat and the Y and the bat and the ball are on the same vertical plane. If they are on the same vertical plane, or the bat is within -1 of the ball. In other words, if the ball is 1 above it, then I move on to the next check to see if then the ball is within the left and right. So in other words, I'm kind of zoning it off and saying, okay, is the ball touching the bat? That's all I'm really doing here. And it returns 1, otherwise it returns 0. So increment, very simple. Just increments the ball. Ball's out of bounds. It just checks to see if it has gone past the screen height +3. And most SDKs and most things are going to have screen height there for you. We have to set it in our case because we have to tell it what's our screen. Now, I think I can actually get it from the console and everything and actually use the entire screen if I wanted to. But I didn't want to do that. I wanted to create my own. I think you can. I don't know for sure, but I think there probably is a way. So decrement lives, this function doesn't even really hold its weight, but it's just better to call functions instead of the variables directly. So, and you notice my draw. The draw method doesn't do anything but leverage that print at XY, and it prints the ball and the Y and uses the ball string. Now, we didn't take a look at our init real closely, but you notice that in the ball string, I just stored a character O, and in the bat string, I stored a series of equal signs. And so all this is doing is saying, hey, wherever the ball, we said the ball is, print that string, print the Y, and those have been updated throughout the game through the frames. And then display score is called, and display score is just drawing at the 0 position with the score and the lines. And of course, we talked about this printx, which is one of the key functions of the whole system to actually draw to the screen. You notice here, display score. All we do is formulate a string here as printf, store it into the buffer, because this is like printf because it takes the printf. If you've done printf, notice that I'm storing the lives and the score, and I store them into here. What happens then with sprintf, which is different than printf, it stores those values into the buffer. Then I can just tell print at xy to write that buffer out to the screen at the 0, 0 position, which is the top left hand corner of the screen. And of course, the ball collides with wall. Very simple. All you're doing is checking to see if the ball has gone past the 0 or past the screen width on the right, and that, those are your walls. The other one is the ceiling. So then ball collides with ceiling, very simple. If the ball has gone past 0, then we know that we've gone past and collides with ceiling. Very simple there. And so capturing the previous position, very simple, just storing your values into another set of variables. This is what I was talking about, to clear the screen here. For clearing the screen, I didn't want to clear everything. I just wanted to make sure that I clear whatever I wrote to the screen. That way it looks like I cleared it, but I'm not really clearing the entire screen. And the entire screen does not need to be cleared because I didn't write on the entire screen. So what I'm doing is I'm writing a couple of blank values. See this? This is a blank value, and I'm just writing that blank value to wherever the ball used to be on the previous frame. And I just clear it, and same thing with the bat. And then I'm also doing that for the scoreboard, and it just clears the scoreboard that way. And of course, display message, very opinionated way to display a message, because I'm not even telling the coordinates. I just pass it the message, and I just say, look, take this buffer, copy whatever message. It has a max limit of 100 characters. Copy the message into the buffer and draw it in the middle of the screen. That's it. Just do that. And of course, cleanup doesn't do anything. Normally in cleanup, you would release all your resources, you would release everything, and then that way you could, clean everything up, close file system, close database, whatever you're doing, you would do it. But in this case, we're not really using any resources. I may have to release the handle, which I'm not doing. I'll have to look into that, but I may actually have to release the handle, and I think I actually do have to release the handle, because since I hit the cursor and you notice that the cursor is still hidden, I may have to release that handle so that way it can go back to normal. So that's something that I probably need to do in cleanup, but I think for this we'll be okay. So that's all your code. Let's take a look at one more thing just to kind of close it out. If you have any questions, just always make sure, just drop it in the comments, and I'd be glad to answer those questions. So let's take a quick look at the summary so we can move on from here. In closing, I wanted to point out that this example is not typically what you would actually use in a real game. Of course, you want to distribute your games and everything, but keep it in the spirit of, if you're a developer and you want to learn and you want to understand the concepts and fundamental, ideas behind all of this, then that means that you have to have some lower level understanding. And I think this simple game does that. Would you create a game in this to distribute? Of course not. You'd probably use something more professional, but this gives you a good foundation to build up from. If you actually wanted to build even some games where they're kind of raw like this, but they're actually with real SDKs, there are some libraries and resources. For example, I believe it's called Simple Direct Media Layer library, which you can find here at the livesdl.org. That library actually allows you to access Direct 3D and sound and everything, and keyboard and resources, and it's really fast. I've used it before many years ago, and it's actually really fast for displaying and rendering and everything else. Of course, you have to learn their API, but if you understand these basic concepts, then you can actually use that should be able to use it with no problem. There's a lot of resources and forums that you can use to leverage that. You can get into more advanced 2D game engines like the Garage Games, Torque 2D. The only thing about those is that they hide so much from you that you're more of an operator. You know how to use it, you know how to create games and everything, but you got to keep in mind they build so much from the ground up that at that point you just more like, if you think of like any other software product like Photoshop or anything. I mean, granted that a lot of people have a lot of talent, a lot of skills and everything in using those software products, but it's more of software use expertise than actually getting down into the programming, because you're going to be creating games with a lot of drag and drop and so on. And of course, don't forget the sounds. We didn't cover sounds because there's probably not much in terms of sounds for that. We probably have to use another library or something to play the sounds. But keep in mind, sounds are a big portion of the game, and those other libraries will provide capabilities for you to do that. So one last point is to make sure to visit the links below if you want the code or the resources. And if you have any questions or comments, leave your comment below and I'd be glad to answer. Make sure to subscribe if you want other videos like this one. I would appreciate that. And thanks for watching.